In this video, we will discuss Fourier Transform and solve many numerical problems from the previous examinations. I will jump over some mathematical steps to save time. You can either pause the video or refer to the PPT given online on my personal website, whose link is given in the description. Now let us start with the video. Fourier series is a frequency domain representation of a continuous time periodic signals, which is given as ft is equal to summation from k is equal to minus infinity to plus infinity fk into e raised to power plus jk omega naught into t, where fk is equal to 1 upon t integral over the time period of the signal ft into e raised to power minus jk omega naught t into dt. Whereas Fourier transform gives the frequency domain representation of a continuous time aperiodic signal. Relationship for the Fourier transform can be derived from the exponential form of Fourier series by considering infinity time period of this signal, that is, t tends to be infinity for aperiodic signals. Here are some important observations in context to the Fourier series pair given by these two relationships. When we consider time t tending to be infinity to make ft an aperiodic signal from a periodic signal. First one is the spacing between fk's tends to be 0 when t tends to be infinity. Secondly, omega naught is given as 2 pi upon t and that tends to be 0. Therefore, the change in the frequency, that is delta omega, is also tending to be 0. The harmonic frequencies given as k into omega naught is also tending to be a continuous quantity written as omega. The spectrum of the signal t into fk can also be written as a continuous quantity f omega. Further, the frequency of the signal, that is 1 upon t, which can be written as omega naught by 2 pi, which is further can be written as delta omega upon 2 pi. Accordingly, the Fourier series expression for fk can be rewritten as t into fk is equal to integral from 0 to t ft into e raised to power minus jk omega naught t into dt. If we put t into fk as f omega and k omega naught as omega, then this relationship will be modified as f omega is equal to integral from minus infinity to plus infinity as t tends to be infinity ft into e raised to power minus j omega t into dt. This is the expression for the determination of the Fourier transform for an aperiodic signal ft. Similarly, the second relationship of the Fourier series, that is ft, can be modified by multiplication and division by capital T on the right hand side. Now, in the right hand side, if we replace t into fk with f omega and 1 upon t with delta omega upon 2 pi, we can modify this relationship by replacing summation with integral as ft is equal to 1 upon 2 pi integral from minus infinity to plus infinity. Here, f omega is called the Fourier transform of the signal ft and ft is called the inverse Fourier transform of the f omega, which is written as Fourier transform pair ft Fourier transform f omega. Now let us take up some numerical problems from the previous examination, where we are required to determine Fourier transform of a gate pulse given by ft, which is equal to a within the time period from minus tau by 2 to plus tau by 2, otherwise it is 0. The Fourier transform is given by the relation f omega is equal to integral from minus infinity to plus infinity ft into e raised to power minus j omega t into dt. If we consider ft in this relationship, it becomes integral from minus tau by 2 to plus tau by 2 a into e raised to power minus j omega t into dt. After integration and putting the limits of the f omega, we get f omega is equal to a into e raised to power minus j omega tau by 2 minus e raised to power plus j omega tau by 2 divided by minus j omega. After bit mathematical manipulations, we get f omega is equal to a tau sinc of omega tau by 2. If we plot f omega with respect to omega, we get a continuous frequency spectrum as shown in this figure. Hence, we can generalize this observation that Fourier transform gives a continuous spectrum for a continuous time aperiodic signal. Now let us consider another numerical problem where we are required to determine Fourier transform of a right-shifted gate pulse given as ft, which is equal to a within the time period from 0 to tau, otherwise it is 0. The Fourier transform is given as f omega is equal to integral from minus infinity to plus infinity ft into e raised to power minus j omega t into dt. If we consider ft in this relation, we will get integral from 0 to tau a into e raised to power minus j omega t into dt. If we integrate and put the limits, we will get f omega is equal to a into e raised to power minus j omega tau minus e raised to power 0 divided by minus j omega. On solving it further, we can express f omega as e raised to power minus j omega tau by 2 into a tau sinc of omega tau by 2. Here, a tau sinc of omega tau by 2 is the Fourier transform of the gate pulse when it was not shifted in time. Once it is shifted in time by t by tau, it is multiplied by a factor e raised to power minus j omega tau by 2. Now let us consider another practice problem where we are required to determine the Fourier transform of an impulse function where delta t is equal to 1 for t is equal to 0, otherwise it is 0 for all the time. Now according to the Fourier transform, f of omega is equal to integral from minus infinity to plus infinity x of t into e raised to power minus j omega t dt. If we consider this delta function in this Fourier transform calculation, this is not an integrable function. Therefore, we consider an alternative approach where we delay the delta function by 0 time and consider an important property of an impulse function, according to which delta t delayed by tau time into g of t, which is an arbitrary function, is going to be equal to a delta t minus tau into g of tau. Therefore, this relation can be rewritten as f of omega is equal to integral from minus infinity to plus infinity delta t minus 0 into e raised to power minus j omega 0, which is now going to be a unity into dt, which is further equal to integral of delta t over the infinite time, which is nothing but equal to 1. Hence, the Fourier transform of an impulse function is going to be equal to unity. Now let us consider another numerical problem where we are required to determine the Fourier transform of a triangular pulse as shown in this figure, and the mathematical function for this triangular pulse can be written using two line equations. One is for positive slope and the second one is for the negative slope as given by this equation. Now let us consider Fourier transform formula given as f omega is equal to integral from minus infinity to plus infinity f of t into e raised to power minus j omega t into dt. If we put this ft in this relation and modify the limits accordingly, we will get f omega is equal to integral from minus tau to 0 a into 1 plus t upon tau into e raised to power minus j omega t into dt plus integral from 0 to plus tau a into 1 minus t upon tau into e raised to power minus j omega t into dt. For simplification, let us consider these both integrals one by one and solve them using integration by parts. The first integral is equal to integral from minus tau to 0 a into 1 plus t upon tau into e raised to power minus j omega t into dt. If we integrate using this formula, we will get a into 1 plus t upon tau integral e raised to power minus j omega t dt minus integral of derivative of the first term, which is 1 plus t upon tau into integral of the second term, which is equal to e raised to power minus j omega t into dt, and the limits are minus tau to 0. If we calculate the integrals of e raised to power minus j omega t in both the sides and putting the limits, we will get finally the first term is equal to a into 1 upon minus j omega minus 1 upon tau into e raised to power plus j omega tau plus 1 upon minus j omega square. Similarly, we can determine the second term, which is coming out to be a into minus 1 upon minus j omega minus 1 upon tau into e raised to power minus j omega tau plus 1 upon minus j omega square. If we add the first and second term, we will get f omega that can be further simplified as f omega is equal to a upon tau omega square into 2 cos of omega tau plus 2. That further, if we simplify, we will get f omega is equal to a tau Singh square omega tau. This is the Fourier transform of the triangular gate pulse given by ft as shown over here in this figure. Now let us determine a Fourier transform of a cosine pulse as shown in this figure, which can be written mathematically as ft is equal to cos of omega naught t within the limits from minus tau to plus tau, where omega naught is the frequency of the cosine wave. Outside the limits minus tau to plus tau, the value of the ft is equal to 0. Its Fourier transform is given by the relation f of omega is equal to integration from minus infinity to plus infinity f of t into e raised to power minus j omega t into dt. If we consider the given ft in this relation, we will get f omega is equal to integration from minus tau to plus tau sine of omega naught t into e raised to power minus j omega t dt. Cos of omega naught t can be written as e raised to power plus j omega naught t plus e raised to power minus j omega naught t divided by 2. For the simplification purpose, let us divide this integration into two parts as 1 upon 2 integration from minus tau to plus tau e raised to power minus j into omega minus omega naught into t dt, and 1 upon 2 integration from minus tau to plus tau e raised to power minus j into omega plus omega naught into t dt. Now let us solve the first integration, which is coming out to be 1 upon 2 e raised to power minus j omega minus omega naught into t divided by minus j into omega minus omega naught with the limits from minus tau to plus tau. When we put the limits and simplify the solution, we finally get the first term is equal to tau into Singh of omega minus omega naught into tau. Similarly, the second term is also coming out to be tau into Singh of omega plus omega naught into tau. If we add both the terms, we will get f omega as tau into Singh of omega minus omega naught into tau plus tau into Singh of omega plus omega naught into tau. The plot of f omega, that is the Fourier transform of a cosine pulse, is shown over here with two Singh pulses shifted at minus omega naught and plus omega naught. Now let us consider another numerical problem which is usually asked in the examinations. Here we are required to determine the Fourier transform of an complex exponential function given by ft is equal to e raised to power j omega naught t. If we try to calculate Fourier transform by the standard formula, the integral value is coming out to be infinity. Therefore, we are required to determine the Fourier transform of this complex exponential function in some other way. Let's consider an arbitrary function xt whose Fourier transform x omega is an impulse function delayed by omega naught frequency. Inverse Fourier transform of x omega is given as 1 upon 2 pi integral from minus infinity to plus infinity x of omega into e raised to power plus j omega t d omega. If we put x omega in this function, we will get xt is equal to 1 upon 2 pi integral from minus infinity to plus infinity delta function of omega minus omega naught into e raised to power j omega t d omega. Now let us consider an important property of an impulse function where a delta function delayed by tau time multiplied by an arbitrary function gt is equal to the delayed delta function multiplied by the gt function value at tau time. Accordingly, we will get xt is equal to 1 upon 2 pi integral from minus infinity to plus infinity delta function of omega minus omega naught. Omega here will be replaced by omega naught according to this property that becomes independent of omega, therefore taken out of the integral and rewritten as xt is equal to e raised to power j omega naught t upon 2 pi into integral of delta function, which is nothing but equal to unity. Hence, by multiplying the equation 1 by 2 pi on both the sides, we will get Fourier transform of e raised to power j omega t is equal to 2 pi delta function of omega minus omega naught. Now let us consider Fourier transform of periodical signals. Periodical signals are not absolutely integrable because there are infinite minima and maximas and discontinuities over the infinite time from minus infinity to plus infinity. Here is how we will be determining the Fourier transform of periodical signals using impulse signal property. The Fourier series representation of a periodic signal xt is given as xt is equal to summation from k is equal to minus infinity to plus infinity x of k into e raised to power j k omega naught t. If we take Fourier transform of both the sides, we will get x of omega is equal to summation from k is equal to minus infinity to plus infinity Fourier transform of x of k into e raised to power plus j k omega naught t. Since x of k is independent of time, therefore we can take it out of the Fourier transform summation from k is equal to minus infinity to plus infinity x of k into Fourier transform of e raised to power j k omega naught t. Since the Fourier transform of 1 is given as 2 pi into delta function of omega. If we multiply the left hand side with e raised to power j k omega naught t, we will get frequency shift in the right hand side. Accordingly, we will get the Fourier transform of e raised to power j k omega naught t is equal to 2 pi into delta function of omega minus k into omega naught. Hence, the Fourier transform of xt is given as x omega is equal to 2 pi into summation from k is equal to minus infinity to plus infinity x of k into delta function of omega minus k into omega naught. This is the Fourier transform of a periodic signal xt. Now let us consider one practice problem to determine the Fourier transform of a periodical signal cos of omega naught t, where omega naught t is the angular frequency given as 2 pi upon the time period of the signal. The function cos of omega naught t can be written as e raised to power plus j omega naught t plus e raised to power minus j omega naught t upon 2. Since the Fourier transform of e raised to power plus j omega naught t is equal to 2 pi into delta function of omega minus omega naught, and the Fourier transform of e raised to power minus j omega naught t is given as 2 pi into delta function of omega plus omega naught. By using the linearity property, we can say the Fourier transform of the signal ft, f function of omega is equal to 1 upon 2 into 2 pi delta function of omega minus omega naught plus 2 pi into delta function of omega plus omega naught. Finally, we will get f omega is equal to pi into delta function of omega minus omega naught plus delta function of omega plus omega naught. If we plot, we get two impulse functions shifted at minus omega naught and plus omega naught, whose amplitudes are pi. Now let us conclude this video by floating some questions from examination point of view. These are the questions asked in the previous examinations. The lower order thinking skills include following questions, and the higher order thinking skill include these questions. Students should solve them on their own. In case of any problem, they can write me in my comment section. I will try to answer their queries. Thank you, my dear students. In this video, we talked about Fourier transform. In the next video, we will discuss about properties of the Fourier transform that will help us in solving numerical problems in less time.